There are several factors which can be measured throughout the course of a reaction in order to obtain data to plot a rate of reaction curve. The first of them being the volume of a gas. If a reaction produces a gas which is released, that gas can be captured by connecting the reaction chamber to a syringe, and as the gas is given off, that gas will of course travel straight into the syringe and of course be collected in here. Now the volume of gas produced over time will of course be increasing because the gas is being produced. Now what we can do is to measure by way of this calibrated syringe the volume of the gas at specific time interval and record that information in a table. We can afterwards use the data from the table in order to plot a curve, and what we'll be doing is plotting volume of gas release as would have been recorded in the syringe with the specific time, depending on what time interval you were using. Could have been every minute, or could have been every 5 minutes, or every 10 seconds. But that information will be recorded in the table, and then we'd plot volume of gas release with time taken. Now that graph would have a specific shape, looking very much like this. So volume on our y-axis and time taken on our x-axis. When that graph is plotted, it will have this general shape, and that is the case because the volume of the gas would have been increasing throughout the course of the reaction. Secondly, we can also measure the mass of the reaction chamber during the course of a reaction, if indeed a gas also is given off. Because if a gas is given off throughout the course of a reaction, what you'll find happening is the mass of the reaction mixture will be decreasing over time. And so what we can therefore do, we can place the reaction chamber or the reaction mixture on a balance, and throughout the course of the reaction, what we can do is monitor the mass of the chamber at specific time interval, and that information can be tabulated. At the end of the reaction, we can then plot mass of reaction mixture against time. That graph would appear after plotting like this. So if we have mass on our y-axis and time on our x-axis, the graph would have this general shape. And it has that shape because throughout the course of the experiment or the reaction, the mass will be decreasing. Thirdly, we could measure the temperature throughout the course of the reaction. There are some reactions in which the temperature of the mixture increases as the reaction progresses. There are others whereby there are significant decreases in temperature throughout the course of the reaction. In any event, such being the case, what can be done? The temperature at specific time interval can be tabulated. So the temperature can be measured at specific times throughout the course of the experiment, and that information be placed in a table. At the end of the reaction, the information collected can then be used, the data collected can then be used to plot a curve of temperature against time. Now, if it is a reaction wherein the temperature increases as the reaction progresses, then what we'll have after plotting the graph, so temperature against time being on our x-axis. So if it's a reaction wherein temperature increases over time, our graph would have this general shape. because there is an increase in temperature throughout the course of the reaction. If, however, it is one wherein there is a decrease in temperature as the reaction progresses, then our graph, after being plotted, will have this general shape, because it's one in which there is a progressive decrease in temperature as the reaction progresses. In addition to temperature, other factors that can be measured throughout the course of the reaction in order to be able to plot a rate of reaction curve would include changes in pH. Because there are some reactions in which there is a fall in pH, a decrease in pH. There are others wherein there is an increase in pH as the reaction progresses. And that can also be measured at specific time interval, and the data collected be used to plot a rate of reaction curve. In addition to that too, we could also measure changes in pressure, especially reactions involving gases, and the data collected can also be used to plot a rate of reaction curve. Now, how can we find the rate of reaction at a specific time on a rate of reaction curve that we have plotted? To do this, we'll have to draw a tangent to our curve, and the tangent is drawn at that point on the curve corresponding to the specific time at which you want to find the rate. Having done that, we'll then use the formula y2 minus y1 over x2 minus x1 in order to calculate the rate. Now, let us see what these y values are and these x values are, and how this calculation of the rate can be performed. Now, if we have a rate of reaction curve as represented by the blue curve here, and we want to find the rate of reaction at a specific time, let's say 46 seconds, what we'll have to do is to draw a line, a straight line from 46 seconds on the time axis all the way to meet the curve, the blue curve here, and we'll place a dot, a point here, and at that particular point where both intersect, we'll then draw a tangent at that point. The tangent here is a straight line, right? And it doesn't cut the curve, it just simply touches it at the specific point where, you know, the straight line would have met the curve. Now, having drawn the tangent to the curve, we can then determine our x values and our y values. So the lower end, at the lower end of the tangent, the x value corresponding to that lower end would be our x1 value. Our x2 value would be our x value corresponding to the upper end of the tangent. So the x value corresponds to this upper end of the tangent is our x2 value. In addition to that, to find our y values at the lower end of the tangent, the y value corresponding to that lower end we'll call our y1 value, and for our y2 value, it is the y value corresponding to the upper end of the tangent. Now, if we label our x2 and x1 value and our y1 and y2 value, we will have them falling as is now seen on screen. Because the scale on the x-axis is as seen, it means that each line on the x-axis has a value of 2 seconds. And so our x1 value then would be, based upon the scale here, our x1 value would fall at 16 seconds. and our x2 value would fall at 70 is midway here, so 72, so it would fall at 74. And in the case of our x-axis, based upon our y-axis, my apologies, in the case of our y-axis, based upon the scale here, each line represents 1 centimeter cube. And so our y1 value would fall at, this being 20, it's 21, 22, would be at 23. And our y2 value would be at 39. Therefore, the rate of reaction at 46 seconds can then be calculated using the formula y2 minus y1 over x2 minus x1. And that will give 39 centimeter cube, which is the value of y2, minus 23 centimeter cubes, which is the value of y1, all over 74 seconds, which is the value of x2, minus 16 seconds, which is the value of x1. Now 39 centimeter cube minus 23 centimeter cube will give us 16 centimeter cubes, and 74 seconds minus 16 seconds will give us 58 seconds. When we divide 58 into 16, we will get 0.28, and the unit here being centimeter cube per second, and that would be the value of our rate at 46 seconds. Now that concludes our presentation. Do hope that you learned. Thank you.